Hi guys. So this is a video about lesson 4.3. I didn't really have slides. I had these guided notes. So it's just so that this video is so that if you're absent or if you were missing the notes, or if you forgot, this is an explanation of what we went over for lesson 4.3. Okay, so refresher on complex numbers. Complex numbers are made up of a real part, which is a, for example, 3 plus 2i. 3 is the real part, and then plus 2i would be the imaginary part. Okay, and in adding complex numbers, and this is the proper form, you write the real and then you write the imaginary second. So adding complex numbers, basically it's kind of like combining like terms with similar variables with the same variable. And so you get 2 plus 3i plus 4 minus 7i. That's 6 minus 4i. So we're combining the 2 and the 4 together, and then the 3 and the negative 7 together. There we go. And then here we have 1 minus 3i. Distribute that negative and combine the real parts, negative 4, and then minus I. 1i, you can have minus 1i if you wanted to. Okay, remember, second part, that I squared equals negative 1. If you don't want to remember that, then you can always start here. We know that I equals the square root of negative 1. If I take this and square both sides, then it ends up as I It ends up as I squared. Square root raised to the second power is going to be itself in the radicand. There you go. Okay, and then I cubed is made up of I second times an I to the 1. So that's going to be negative 1 times I, which is negative I. And then I to the 4th is a I to the 2nd times a I to the 2nd. So that is going to be a negative 1 times a negative 1, which equals a 1. And once we find out the factors of I to the 4th that make up that particular exponent, or the divisibility of 4, then we can simplify C, D, E, and F very easily. Okay? So let's go ahead and FOIL. And we're just taking the 2 and multiplying it by the 2 terms. So we get 2 minus 8i plus 3i minus 12i. Right? 2 times 1, 2 times negative 4, and then 3 times 1, and then negative 12. Yep. And you end up with a 2 minus 5i. And that's going to become a plus 12 of this I squared. And then you end up with a 14 minus 5i. Once again here, we have an I times a 3. I mean a 2 times 3 and a 2 times negative 1. 2 times 3 is 6. So that's a negative 2i. That's a minus 6i. And then a positive 2i to the 2nd. So you end up with a 6 minus 8i minus 2, 4 minus 8i. There we go. Now to simplify these, we can find out how many times 4 goes into 18? So I to the 4, and it goes in 4 times. And we have a remainder of 2. Should be right. 4 times 4 plus 2 should be 18. And once we figure that out, that just becomes 1 times I to the second is going to be a -1. So this ends up as -1. Let's see how many times that 4 goes into 31. I think it's 7 times. And you're left over with I to the third. So that's again, this is 1 times -I. So this ends up becoming -I. Okay. How many times does 4 go into 331? It goes in 77 times. Oh, whoops. No, you could rewrite it like this if you wanted to. It doesn't really matter, but then we don't know what 77 is. So you can do 4 and 77, because basically what we're doing is this I to the 4th inside is going to become 1, and 1 raised to the 77th power is just 1. And we have I to the third left over. I to the third is -I, so -I. Okay, 4 once again, I to the 4th. So that goes in 10 times, I to the third. Once again, -I. Okay. Next, dividing complex numbers. So first of all, it says find the conjugate. Well, A and B find the conjugate. Okay. Now conjugates, okay, are, here's the real. It's going to be, the real is +3, the real part. And the imaginary part is -1I. I mean, not T, but I. Okay. Now, the conjugate is the real keeps its sign, but the imaginary 1I has an opposite sign. Okay. Now this is, you can rewrite this as 4 plus I, and it's going to be 4 minus I for the conjugate. So we need the conjugates to multiply. We can't have an imaginary complex number in the denominator. So we're going to take that and we're going to multiply it by its conjugate. And conjugate is kind of like a difference of squares. So if you have x squared minus 9, it's going to be made up of factors x plus 3, x minus 3, and x plus 3. And because this middle term is missing, there is no middle term. And the reason that there is no middle term is that once you FOIL this or simplify it, that the -3 and the +3 are going to cancel each other out, become 0. So therefore, it's not going to have a middle term. And just like that, the conjugate of this, 1 plus I, when you multiply 1 minus I by it, it'll cancel out that middle term. So let's go ahead and multiply. So we have a 3. And that is going to be a plus 3I minus I, and then a minus I squared. And then we have a 1 plus I minus I squared. So this is going to give you, whoops. So this is going to give you, let's see, a 3 plus 2I plus 1 over 1 minus or plus 1, because this ends up becoming -1. This, so -1 times -1 times -1. So you end up with a 4 plus 2i over 2. And then you can simplify it by factoring a 2 out. 2 plus I over 2. So you get a 2 plus I for your final answer. Okay. For D, okay, we're going to go ahead and I'm going to rewrite this 1 plus I, because what I see down here is that it's not its proper form. 3 plus I multiplied by 3 minus I over 3 minus I. That is the conjugate. Okay. And then once you do that, go ahead and FOIL. So 3 minus I plus 3I minus I squared. 9 minus 3I plus 3I minus I squared. And let's go ahead and simplify. So that becomes 3 plus 2I plus 1. And then 9 plus 1. So you end up with a 4 plus 2I over 10. I'm going to factor out a 2 from the top. 2 plus I over 10 equals 1 and 5. 2 plus I over 5. Okay, and good job. Okay, now how are we going to use that? Because that was a review over Algebra 2. How are we going to use that? And so the fundamental theorem of algebra basically says that every non-constant polynomial has a 0 in the complex number system. Okay, so basically the fundamental theorem of algebra says, for example 1, the degree right here, it's a degree 3 polynomial. So that tells us that it's going to have 3 complex roots. Now, complex roots, a plus bi, they could either be imaginary, have the actually imaginary counterpart. So it could be something like 3 plus 2i. Okay, if there exists a 3 plus 2i, then there has to be a 3 minus 2i. And then it could be just real. And that is included in the complex roots, because if I rewrite this and say it's something like 4 plus 0i, then that's just 4. The imaginary counterpart is just 0. Okay, so once again, all this says is there's possibility of 3 roots. They could be imaginary, they could be real. And that's what the fundamental theorem of algebra says. Okay, so let's go ahead and find all the zeros. How do we find all the zeros? Well, first we can set this equal to 0, or the y equal to 0. Let's try grouping them together. Since there's 4 terms, so x to the second, so x minus 3 plus 1, x minus 3. We can group them. We have an x squared plus 1 and an x minus 3, right? Okay, so we have this, but then we're not done, because we have to find all the zeros this time. We have to find the complex roots. We have to find the imaginary counterpart. So I can take each of these, x squared plus 1 equals 0, x minus 3 equals 0, and find the zeros. X squared equals negative 1. Square root both sides, so x equals plus or minus, that's going to be I, and x equals 3. So the zeros are going to be x equals plus or minus I, and 3. Notice if we have a plus I, we're going to always have its conjugate, minus I. They go together. Okay, now the complete factorization x minus 3, but we have to show this as a factor. This is not sufficient. Okay, that's not factored. That is not made, x squared plus 1 is not made up of two multiplication of two factors. So how do I do this? What I could do is set this x plus I and x equals minus I. And when we did this, we set it equal to 0. We had the right-hand side equal to 0. How do you make that right-hand side equal to 0? When we move this plus I to the other side. So it's kind of getting messy. I'm going to redo this. So we had x equals I. So the right-hand side has to be 0. So I'm just going to move this I to the other side and have this side, the right-hand side, equal to 0. There is one of my factors, x minus I. Well, if we have x minus I, we know that we have to have the conjugate. And we can actually do this, have that right-hand side be equal to 0, move this to the other side, so x plus I equals 0. Those are all of the factors. And good job. Okay? So once again, we know that we're going to have 3. Okay? We have to find all the zeros. Let's go ahead and set this equal to 0. Okay. How do we do this? Well, there isn't any other way. We have to figure out, we have to use the rational root theorem and do plus or minus 1, plus or minus 2, plus or minus 4. There's no way to factor this. Okay, and then plus or minus 1. So we know that the rational factors could be plus or minus 1, plus or minus 2, and plus or minus 4. Okay, so let's go ahead and use synthetic division. So we have a 1, a 0, a -2, and a 4. Let's try 1 to see if it works. Bring 1 down. 1 times 1 is 1. 1, 1, -1. Nope, it doesn't work. Let's try 2. Okay. 2, bring down the 1. That's not showing up very well. 2, bring down the 1, 2, 2, 4, 2. It's 4. Let's go ahead and try a negative number. Let's try -1. 1, -1. -1, 1, -1. Nope. Let's try -2. We're getting closer. -2, 1, -2, -2 times -2 is 4. And that's going to give you a 2, -4, and 0. And we have a x squared minus 2x plus 2 equals 0. Now, we can use the discriminant to figure out if this is factorable. And we have 4 minus 8. Nope, it's not. Okay, and that's going to give us a -4. So I'm going to use the quadratic formula, 2 plus or minus square root. I already have what goes inside of the radicand, 2, and that's going to be x equals 2 plus or minus 2i. Okay, I'm going to go ahead and factor out a 2 there, and you get 1 plus or minus I over 2. So x equals 1 plus or minus I. So don't forget that 0. Those are the zeros, -2 and 1 and plus or minus I. Now let's go ahead and find the factors. Well, x minus 2, x equals -2. bring that, move it to the left-hand side. So that's going to be x plus 2. There's a factor here. Let's break this up as plus or minus. X equals 1 plus I. X equals 1 minus I. Move both of these to the left-hand side with a 0 on the right side. So x minus 1 minus I. Move that. X minus 1 plus I. Okay, good job. So conjugate zero theorem, which we kind of went over. Okay, when they tell us to write a quadratic with those as the roots or zeros, okay, there's a couple of ways to do it. I always prefer option 1. Since I gave you the 3 options, you can use it either way. Okay. So let's go ahead and do example 4. Let's go ahead and put all of these in the given form. Okay. And so here we have x equals 4, x equals -1, x equals 2. And they didn't, well, it says to put it in standard form here. And then I'm just going to make that right-hand side 0. Move that term over to the other side. So I get x minus 4, x minus 4, x plus 1, x minus 2 equals 0. Okay, and then let's go ahead and write it as a polynomial. P to the x equals, and I have to multiply, so that's going to give me x minus 4. Let's go ahead and multiply these two. X squared minus 2x, minus 2x plus x minus 2. Go ahead and simplify. X squared minus x minus 2. X cubed minus x squared minus 2x minus 4x squared. X cubed, x squared, just checking. X cubed minus x squared minus 2x minus 4x squared minus, and that's plus 4x, and that's a plus 8. A piece of x equals, after we've simplified it, x cubed minus 5x squared plus 2x plus 8. Okay. One way of checking is to actually use this as, put these as inputs. And if you get a remainder or an output of 0, then you know that you got the right answer. Because using the remainder theorem. So an input of 4, -1, and 2 should produce a 0 as the output. Because that makes sense. This is y-intercept. I mean the x-intercept. Okay. Now, multiplicity of 2. So that means x equals -2, x equals -2, x equals 3. So that's x plus 2, x plus 2, x minus 3. So that's x squared plus 4x plus 4. Multiply that by x minus 3. So we have an x cubed plus 4x squared plus 4x minus 3x squared minus 12x minus 12. And so piece of x equals x cubed plus x squared minus 8x minus 12. Okay, good job. Next, we have x equals 1, x equals, break this apart, 2 plus the square root of 5. And x equals 2 minus the square root of 5. And then x minus 1, x minus 2 minus square root of 5, x minus 2 plus the square root of 5. And then let's go ahead and multiply these two together. Okay, and the way that I did it was, so we had an x or minus 2. Go ahead and group those two together. Okay, and that's going to be squared, and then minus squared. And since these are difference of squares, you can kind of see that. Trying to look for a highlighter. Oh no, I don't want that. So we have x minus 2 and an x minus 2. And then we have a, oh, that doesn't show up. And then we have a minus a square root of 5 and a square root of 5. And once again, if you compare it with x minus 3 and x plus 3, that's going to end up as x squared, or you can square that first term, and then a difference between that and 3 squared, kind of like that. And that's where this comes from. Okay, if you realize that this is one term and that is another term, and group them in that way, then we can use the properties of difference of squares and create a prior to factoring. What is the opposite of factoring? A expression such as that. So when you have this, you have x minus 1, and then x squared minus 4x plus 4, and then minus 5, kind of like that, and then x minus 1, and then you have an x squared minus 4x minus 1, x cubed minus 4x squared minus x, and then minus x squared plus 4x plus 1. So a piece of x equals x cubed minus 5x squared plus 3x plus 1. Okay? Good job. Okay. Now, it's getting a little bit complicated. X equals 2 plus 3i. X equals 2 minus 3i. X equals 1 plus square root of 7. X equals 1 minus the square root of 7. X minus 2 minus 3i equals 0. X minus 2 plus 3i equals 0. X minus 1 minus square root of 7 equals 0. And x minus 1 plus square root of 7 equals 0. Okay, let's go ahead and combine these two together. X minus 2 minus 3i. X minus 2 plus 3i. X minus 1 minus square root of 7. X minus 1 plus the square root of 7. Now, once again, we can take the x minus 2, and the minus, or 3. Let's go ahead and 3i and the 3i, and group those two together. And so you end up with an x minus 2 squared, difference of the two, 3i squared. And over here we have an x minus 1 and an x minus 1 and a square root of 7 and a square root of 7. And group those two together, x minus 1 squared, difference of square root of 7 squared. Okay, so we have an x squared minus 4x plus 4. And that is going to be minus and 9i squared, x squared minus 4x plus 4. That's going to be a plus 9. So x squared minus 4x plus 13. And this is going to be x squared minus 2x plus 1. And that's going to be a minus 7. So x squared minus 2x minus 6. And let's go ahead and try to multiply this. I had a really hard time trying to multiply this. P of x equals, try to start with the x squared, x to the 4th minus 2x to the 3rd minus 6x squared. And I just distributed it over to these. Let's do the negative 4x. I'm going to run out of space. Negative times a negative is positive. That's 4 times 2 is 8. X squared. Oh, I skipped one. That's going to be negative here and here. Okay, negative 4x to the 3rd. And then plus 8x to the 2nd. And then minus 24x. Now let's do this one right here. That's going to be a plus 13x squared minus 26x and a minus 13 times 6. 78, negative 78. So we have piece of x equals x to the 4th, x to the 3rd, and x to the 3rd, negative 6, x to the 3rd, x to the 2nd, x to the 2nd, x to the 2nd, right here. So negative 6 plus 8 plus 13 is a positive 15x to the 2nd. And then we have a negative 24 minus 26, which is a negative 50x and a minus 78. Okay. Good job. I think that's all the problems. Got it. Good job, guys.